In this video, we're going to talk about writing an equation of a parabola. We're going to look at a couple different scenarios where that might be useful. And we're going to start with this example right here. So write the equation of the quadratic function whose graph is shown. Basically, we want to write an equation of a parabola that would have this graph. The easiest way to do this is to use the vertex form. And I've listed it here for you. We've talked about that previously in the previous video, right? So a parabola can be represented by two different formats for a quadratic equation. This one is factored, and it features the vertex in a very easy place. So it makes it really easy to construct the equation if we use this format. This is the only format we're going to use. Okay. And we've spent a lot of time talking about this format. So the H and the K, if you'll remember, those go together to make the vertex. Let me just jot that down. So because this relates directly to the graph, we could reason out the coordinates or the values for H and K very easily. Okay, let me add in my arrows here. All right, so I think you can pinpoint the vertex. It's right here. So that would be the point 3, 5. So if the vertex is H, K, and the vertex on the graph is 3, 5, it follows, right, pretty easily that H must be 3 and K must be 5. So let's put those into our vertex form. So now we have y equals, we don't know A yet, x minus 3 squared plus 5. Okay, and actually A is the only thing that we need. We want to write an equation, so we would like the x and y to continue to be variables in our final answer, but we need a number in there for the value of A. So to find the value of A really becomes the big job here. So all we have to do, let me write this down, I guess. So to find A, we're going to choose another point on the parabola, not the vertex. We don't want to choose the vertex because plugging in the vertex will create a 0 here, and it will cancel out our A. We would like to solve for A, so not the vertex. And then we're going to plug in the values for x and y and use that to solve for A. Okay, so let's do that. I'm going to bring it down just for a second so we can look at the graph. Now, it doesn't really matter which point we choose. A point that we can easily tell is on the axis would probably be good. Here's a point right here. We'll try to use this one. Okay, so this would be the point 6. -4. Okay, so let's do that. Let's plug in the value 6 for x and -4 for y. Right over here. We're leaving A as a variable because that's what we're trying to solve for. Now the important part here is to use the order of operations. That can be kind of crucial. If you don't do it in the correct order, you're not going to get the same answer every time. So we would want to work from the inside. 6 minus 3 would be 3 squared. Three squared is 9, and we do the multiplying first. 9 times, this is 9a. It would not be appropriate to combine these numbers together, right? Those are the sorts of things that make math teachers cry. Okay, so do it like that. That's in accordance with the order of operations. Then we would like to get a by itself. So we can subtract this 5 over. And divide both sides by 9. Looks like a must be -1. Okay, and remember our goal here was to write an equation. So I'm just boxing in all the important variables that we have found the values for. So now we want to write our final answer in this vertex form. So we have y is -1 times x minus 3 squared plus 5. And if we think about what a does to the graph, I'm pulling on previous skills, right? But if the value for a is negative, then the graph should open down or be reflected. And I think we can see that in the picture that we were given. Okay? So if we're given a graph, this is a really good way to create an equation for a parabola. All right, so I want to extend this a little bit farther and show you some of the patterns that are in the table when we are working with parabolas. So we'll call this building quadratic models. Right, we have already talked about building linear models where we looked at the pattern in the table. We had a consistent change in x that produced a consistent change in y. Okay, and there's a different kind of pattern for a quadratic, and it's kind of interesting. So we're going to treat this sort of like we did when we looked at a data set and we tried to fit an equation for a line to that data set. We're going to do the same thing here, but now we're working with quadratics, so we're trying to fit a parabola, right? Our goal is to find a parabola that comes the closest to passing through all of our data points. We would love it if they all lined up right in the parabola shape, then we could come up with an exact equation. Sometimes that's possible, and sometimes that's not possible. We've talked about the different reasons for that. Collecting data is not always exact. Outliers and things of that nature. Okay, so I want to kind of address this like we did for linear functions and look at things that are exactly quadratic and then talk about what we can do when it's approximately quadratic. So if the data we have in the table is exactly quadratic, there's a really interesting pattern. So first of all, it's important to notice that in order for this to work, the x's have to be in some sort of steady, consistent pattern. And these are, right, they're going up by 1. Okay, and then we can look at the change in y. So in this table, the change in y from 25 to 40 is going up by 15. From 40 to 45 is going up by 5. From 45 down to 40, it's going down by 5. And then from 40 down to 25, it's going down by 15. So if these were the change in y here, if they were all the same number, we could say that it was a linear function. This one's definitely not linear. For a quadratic, we actually do this process twice. So the change in y here is called the first difference. the quadratic pattern shows up when we do what's called the second difference. The second difference looks at the change in these numbers here. So it's the change in y. That sounds really silly, but that's what it is. So to go from 15 to 5, we're going down by 10. To go from positive 5 to negative 5, we're going down by 10. And then to go from negative 5 to negative 15, we're going down by 10. And look at that. The second differences are all the same. So this is how we can test to see if a data set is exactly quadratic. These points will line up right on a parabola. That's kind of an interesting pattern to identify. Okay, so the next step, once we've identified that it's exactly quadratic, we would like to have a general rule to describe this trend, these patterns that we're seeing. Right, and so the rule would be an equation for a parabola. This is a lot like what we just did. Okay, so I'm going to give you a lot of information when we do this. I will always give you the vertex. I didn't label that here. I probably should have. I'm going to circle it. Okay, so this point in the middle, this is the vertex. And then we can look at the value for A and talk about how it's related to that second difference. Okay, so let me pencil in here that the vertex is the point 3, 45. And we can go ahead and put that in. So we have Y. We don't know A quite yet, but this is our H, the 3 here, and our K must be 45. Okay, and we just practiced this idea, how to find the A, right? So it's not any different this time. We can pick a point on the table, not the vertex, but some other point, substitute that in for X and Y, and use it to solve for A. So I'm going to pick the first point listed in the table here. Not for any good reason. Any of these points would work the same because this parabola is going to pass through all 5 of these points. Okay, so I'm going to put in the 25 for my Y. I'm solving for A. And I'm going to put in the 1 for X. Okay, and then I can solve this equation for A just like we did a minute ago. And just like I warned last time, the same warning here, the order of operations is very important. So negative 2 squared is multiplied by A, so that becomes 4A plus 45. And then we can solve for A. It looks like A is negative 5. Okay, now I wanted to show you us working that out so you could kind of have a method that you can trust. This value for A is also always going to be half of the second difference. It's not a coincidence. It's not just this problem. We could look back to the previous graph and make a list of points and find the second differences, and we'd see the same phenomenon, which is kind of interesting, right? Okay, so our equation then becomes y equals negative 5 times x minus 3 squared plus 45. All right, so this would be exactly quadratic. And now you understand the pattern of the second differences. And that's always going to hold true for a parabola. Okay, so let's talk a little bit about something that is approximately quadratic. So in this case, maybe these points don't line up exactly on a parabola, but they're close. They cluster around the parabola, right? Maybe we have sort of this cloud of data, and it is not, it's not an exact shape, but we can definitely see a trend. And for a parabola, it may or may not be the whole bowl shape. It may just be one side. That counts, right? We could still use the equation to predict that one side of the parabola. That would be okay. Okay, so we could do a similar kind of thought process around this data set. We could look at the second differences. So here's, well, I guess maybe, you know what, we do not have, we do have an x value that's repeated, which is okay, but other than that, oh, and down here, but other than that, they go up by 5s. We'll have to think about that actually when we look at the second differences, won't we? I didn't really think that through. So this goes up by 5, up by 5. This one does not go up, but this one goes up by 5. I might need to go back and find another example for this so that we can do a good comparison. Not sure how well the second differences would apply here. So at this point, maybe we'll just say, hey, this is approximately quadratic. Okay, and let me talk about how we're going to deal with that. Very likely I will come back and redo this video with another example where I can show you that the second differences do not come out to be the same. Okay, and we're going to deal with it in a very similar way that we dealt with something that was approximately linear. We're going to do a quadratic regression, which basically means we're going to look for a parabola that comes the closest to touching all of the data points. And so we can do this with our calculator in a very similar fashion. I guess I'll talk through this and then I'll put the table and the calculator together. So we're going to enter the data in the same way we did for a linear regression. We're going to click on the stat key. There's menus at the top. The first menu is edit. And the first choice in that menu is edit. And then we're going to see some lists. We're going to enter our X's in list 1 and our Y's in list 2. Okay, and then to do the quadratic regression, we're going to go back to the stat key. We're going to arrow to the right once for the calc menu. For the linear regression, it was choice 4. For the quadratic regression, it's choice 5. Okay, and then we're going to get an equation for a parabola that looks like ax squared plus bx plus c. So let's try that. Okay, so I'm going to hit the stat button. I'm going to hit enter for edit. Then I'm going to put all of these speeds, right? This is the speed that we're driving and the miles per gallon that we get when we drive that speed. This is for a Toyota Camry. Okay, so let's type these in. I got that right. Okay, and then just like we've said many times, I always check to make sure they're even at the bottom, so I didn't leave any numbers out. All right, so there's my data. The next step is to go back to the stat key. Then we're going to arrow to the right once for the calc menu. And the quadratic regression is choice number 5. So you can either hit 5 or scroll down to 5 and hit enter. And we can pretty much say the same thing here as we did for linear regression. My calculator is a little bit older, so it's going to put the command on my home screen, and I'm going to hit enter. If you have a newer calculator, it may show you a bunch of things there, where your data is and so forth. So you will scroll all the way down to calculate and hit enter. Okay, and then these are the values for A, B, and C that fit into the equation for this parabola. So let's write those down. We're going to round to 3 decimal places. So for this one, we have negative 0.017 x squared plus 1.935 times x. Okay, and I guess I already put in the minus there, and generally that would be a plus, and C would be negative, but in this case, I guess I was anticipating that C was negative. So this would be 25.341. Okay, so now you know how to find an equation for a parabola if you have a data set that is close, shows a parabola-like trend, but maybe doesn't fit exactly. You can use a quadratic regression. Okay, one more problem that I thought would speak to this well, based on the idea that we want to use a parabola to model a situation. Here's a kind of a common problem that we can look at. It says a man has a farm that is next to a river. Suppose he wants to build a 3-sided rectangular pen for his cows, with one unfenced side being the river. He plans to use 500 feet of fencing. Okay, and then our first task is to use this information, or using this information, create a mathematical model that you can use to calculate the area of the pen based on its width. Okay, so basically a mathematical model. This is, we want to create an equation. Okay, and I want to be able to calculate the area of the pen based on its width. So I'd like to use a variable to represent the width, because I want my equation to involve the width. So I'm going to let W be the width of this pen. Okay, and I've got a picture here. So the places where we're going to put fencing are all the places that are not on the river. So I'm going to put a fence here. I'm going to put a fence on this side. And on this right-hand side. But I am not putting a fence on the river, right? I guess we're assuming that the cows are not going to go into the river unless they absolutely have to. Okay, so if we were to label this, right, here are the widths of this. It's a rectangle missing one side. All right, and then I need to come up with a way to represent the length, because it asks me for an equation that's just based on the width. So what I'm going to do is I'm going to use the fact that we have 500 feet of fencing total, and I want to use all of that. That's kind of the implication here, right? So if I added up, let's say this is my length. I have W plus the length. I want that all to add up to 500. It's the same as 2W plus the length. So if I want to come up with a way to represent the length, I can subtract this 2W over to the other side. And my length must be 500 minus 2W. Okay, so that's maybe step one. If you were going to break this into parts, I had to talk about the length of fence that I wanted to use, and I used that fact to help me write down a way to represent the sides of this pen with using just the variable for the width. All right, I guess the second part here is the fact that we want to use, we want to create an equation for the area. This is a rectangular pen, so the area is the length times the width. So here's where my variables are going to come in. So I can represent the area of this pen. 500 minus 2W is what I'm using for the length. And W is what I'm using for the width. So I can distribute this W and use that to come up with a formula. So I'm distributing. This will be 500W minus 2W squared. Okay, now usually when we have a variable squared, we kind of list it in descending order from highest exponent down to lowest. So let me rewrite this as negative 2W squared plus 500W. Okay, and we've done our job. We've created a mathematical model that we can use to calculate the area based on the width. So if I'm given any number for the width, I can calculate what the area of the pen would be. All right, so that was the first part of this question. The second part says, what is the maximum area that can be fenced by creating the pen in this way? Okay, now we're taking this a little farther. Let's think about this relationship, right? I don't have to graph this per se, but think about what the graph shape would look like. How are the width and the area related? Because I have a W squared here, there's a parabola going on, all right? In front of the W squared is a negative 2, so is my parabola opening up or opening down? Let's make a sketch of that. The W is acting like my X. The area is acting like my Y. And I don't really know exactly all the details about the graph, but I do know that it's shaped like a parabola and it's opening down. So let's go back to the question. What is the maximum area that can be fenced by creating the pin? Can you find a maximum in this picture? Yeah, it's totally the vertex. And the coordinates of the vertex are going to be W, comma, A, because W is acting like X and area is acting like A. All right, so now we have to kind of go back to some other skills. We didn't cover these skills in this particular video, but we have discussed them if you're watching the videos in order, right? We're going to use the minus B over 2A idea to calculate the vertex. All right, and I'm using the variable W because W is acting like X. That's my independent variable. I can choose any W I want. I'm going to use this formula to find, right, this would be my A, this would be my B, C would be 0 because I don't have a number added here. I'm going to plug that into my equation. Okay, so negative 500 over negative 4. I probably should be able to do that in my head, but I'm going to use my calculator. It gives me 125. Okay, and if we go all the way back to the top, the width here is in feet. So if I make the width 125 feet, that's going to give me the biggest area. This question doesn't ask me for the width, though. It asks me for the area. So I'm going to go back to my formula up here in part A and plug in the width. I'm definitely going to use my calculator for this part. So this part gives me negative 31,250. This part gives me 62,500. So it looks like we get 31,250. This is going to be square feet, right? Because each side is given in feet. All right. Well, that ends this video. I've given you several examples of how a quadratic function, how we can make an equation out of some information about a relationship that is parabola shaped or quadratic. So I hope you found this useful.